So we defined at the derivative at point of a function at point x0. So if you remember, it was the number f prime x0 that we know how to compute by considering the limit of the variation of value of f at x0 over x minus over x, okay, as x approaches x0. We saw also it's the same thing. We can also write it differently. The limit of x0 plus h minus fx0 over h by setting h as x minus x0. So if you look, what we remark here is that we can repeat this calculation for each x0 on a certain interval. Imagine that for each x0 belonging to an interval, fx0 exists. That means it's finite number, it's well defined. Then the relation, the assignment that assign for x the number f prime at x0. So I said f prime, not f. Okay. Suppose that we have for each x0, okay, we have the number exists, okay, the number derivative of f at x0 exists. Then this correspondence is a function. And as for each x0, okay, also if I write here for x in the interval instead of x0, particular x0, okay, so we have x like that is a function that we will denote f prime, okay. So we will set the following definition, okay. So the function f defined by f prime at x given by the limit of the variation of f, so x plus h minus fx over h as h approaches 0. The function defined by f prime, okay, is called the derivative of f with respect of x. We use also this notation df dx, okay, at the point x, okay, at the point x. The function defined by f prime is called the derivative of f with respect of x at the point x when the limit exists. Okay, so here is the definition. So like that we have a new function, okay. You have a new function and it has we will see later the importance of introducing such function. We will be able to get more information on our function and be able to interpret more precise behavior on the function. So this is the importance of this new function. So the word derivative, why we call it the derivative of f, this is because this function is defined using from the function f. Okay, so it is derived from f. It is a consequence from that we deduce from f. This is about the terminology. Okay, so let's find the derivative of some examples. Okay, so let's do a practice and find some. The first one, so the first example, let's consider look for of the derivative of the following function. So let's consider fx equal x3, for example. Okay, and find the function, the derivative. Okay, so we know that f prime by definition will be at particular x will be the limit, the variation of f. Okay, which as x as h approaches 0. So it will be the limit of x plus h cube minus x cube over h as h approaches 0. We can develop the cube. Okay, so we will have x3 plus 3x2h plus 3 xh2 plus h3. So you can develop, make the product slowly and get it. Okay, so here I see that I can eliminate, simplify by x3, and I have also a factor of, okay, factor by h. Okay, okay, so it will be the limit, let's factor by h. So we will have h 3x2 plus 3xh plus h2 over h. So simplify again. Let's simplify by h, by h, and then use the limit. Okay, so we will have its limit as h approaching 0 of 3x2 plus 3xh plus h2, which is equal to 3x2. So here is my function derivative. Okay, so let's also try just to see what information we have. Okay, so if you look, we know the graph of the x3, the function x3. Okay, so here is the graph. We can do it here. So it passes through point 1 1. Okay, and minus 1, and we know the shape, global shape of this function. Okay, this is the origin, so it does something like that. Okay, and it goes up like that. Okay, okay, now if you look, now let's look just this. Okay, if we look now at so we can imagine at each point x the slope of a tangent at this point. At each x we can imagine, we said, a tangent line. Okay, sorry, I lost this line, part of the curve. So for each x we can assign fx and imagine lines. So let's just try to make some of the lines, the tangent lines. You see, tangent line. I can imagine some tangent lines, and I see the slope here is positive. All my lines are having this direction. Here the tangent, here the slope is 0, the tangent is horizontal. Here the slope is still positive. Okay, still positive. Here it's larger. Here it is here it's large. It is larger at this direction. It's larger. And then it becomes, then it decreases, it is less until it then it is 0, then it is increasing. So if we try to imagine the graph of approximately, just guessing, so I will have then the graph of f prime will have large positive values, okay, positive, then they decrease until they reach 0, then they increase, okay, they increase. So this is I am expecting the graph of f prime, and the one we have here, the blue one, so the graph was the graph of f, okay, this is the graph of f, okay. So where f prime, where f prime of x is positive, the tangent line, the tangent at x is the slope, okay, the slope is positive, the slope, or the tangent the behavior is up also, we can say that, okay. We can describe this again. Now let's continue. So where f prime x is negative, the tangent at x is down. Where f prime x is 0, the tangent line at x is horizontal. So you see, the function f prime allow us to get information on the shape of the function. Let's now explore another example. What can we say about an example like this one? Another example. What about fx equal the absolute value of x? We know also the graph of fx, okay? We know the graph, you know how it is, pass through the point 1 1 and minus 1 1. Okay, so this is my function, okay? It has the value x if x is positive, and minus x if x is negative. This is what we know. Okay. Now, so if I work here, if I take an x here greater than for x, it's clear for x positive, fx is equal to x, so it's polynomial or power function, so we know that the derivative will be 1. For now an x that is negative, okay, the function fx is we don't know, we didn't do the calculation. Let's do it. I think we need to do it. I thought we did it before, so just let's apply the definition of derivative, and we will see that it is true. So let's, for an x positive, so I will have a limit as h approaches 0 of the difference x plus h minus absolute value of x over h. Now, if your x is positive, let's say it's here, when you add an h that is very small, x plus h here or here, okay, x plus h, so x is positive, you add an h positive or negative but small, still your x plus h remain in this area. That means remain greater than positive, because your h is going to 0. So you can remove the absolute value, because this quantity, because so here this quantity is positive for h very small. Okay, for h very small, that's why you can remove the absolute value. Okay, let's continue. X is positive, so the absolute value is x over h. And now you see we can simplify and get the limit of 1, which is 1, as h goes to 0. Similarly, for x negative, we will have limit absolute value x plus h minus absolute value of x over h. What happens now? If my x is located if my x is located here, somewhere here, okay, if my x is located here, then the x plus h, I can choose an h very small, it will remain here, this area. So we will have then again we can, so we will have something negative. Okay, so it will be equal to the limit h to over 0, so it's minus the x plus h. X is negative, it's minus x over h, which is the limit of minus 1, which is minus 1 as h goes to 0. So we see that the derivative will be, this is my f prime at x, and this is my f prime at x also for x negative. Now for x equals 0, we have to be careful. So here, why I didn't include 0, because when I compute the limit, I need to be interior. I don't, I need to work around the point, the considered point. So when I am at 0, my function is taking different forms. So I need to discuss this point particularly. Okay, so I will compute the limit. So it's 0 plus h minus 0 over h. So it's the limit, absolute value of h over h. Sorry, what is that? Okay. Absolute value of h over h as h approaches 0. And here you see the limit will be limit as h approaches 0 plus, it will be h, because h is 0 plus, that means h is remain positive, which will be the limit of 1, which is 1. Now the limit as h approaches 0 minus of, we will have then minus h over h, will be the limit of minus 1 equal minus 1. You see, so we have two behaviors, different behavior, depending on h to the right, or so that means this limit doesn't exist. So f prime at 0 do not exist. Okay, still we have like two slopes here, one, so you will have a tangent here, and another with slope minus 1, we have another tangent. Okay, we can call them this as f prime plus 0, the right derivative to the right, here the derivative to the left of 0. So we define also this kind of limit to the right and to the left. Okay, those are, yes, when h goes to 0 plus or 0 minus. Okay, so let's give the definition since we spoke about it here. Okay, let's add the definition here. So we define f prime minus x as the limit as h approaches 0 minus fx plus h minus fx over h, and we define the limit f prime, or let's write it here, and f prime plus at x is the limit as h approaches 0 plus fx plus h minus fx over h. Okay, so we have this right limit, left limit for okay, for the derivative. Okay, so geometrically this will be a slope to the line tangent to the right. Okay, and this is also will be a slope, okay, to the right, to the left of the point. Okay, and so, and it gives us so here doesn't exist, so we have an example of function that is not differentiable but has a corner. Okay, so this is, we call it also a corner or cusp. Okay, and the last now example comes from the following property. We need to know the following property. Let's add this property. I think we'll call it theorem. Okay, so we have the following theorem that says if f is differentiable, then f is continuous. F differentiable at x0, then f is continuous at x0. This is important because it tells us something important. Okay, it tells us that if so whenever f is differentiable, necessarily it is continuous. That means if you have the set of continuous function, set of C0 functions, okay, the function that are differentiable are included is a subset. Okay, this is the set of differentiable functions. Okay, differentiable functions. So it's smaller, it contains less functions than continuous. That means differentiability is a property that is more restrictive, that is asking more than continuity. Okay, and of course the proof is very easy. It uses the character, nothing really, it's very easy. Look, it's more technical. x0, we can always write it as fx. It's tricky, more a trick. Look what I did here, and write, multiply and divide. Why? Because this quantity, I know it. This one, I know that it approaches f prime at x0 when we have differentiability. It exists. Times this one will approach what? x0 minus x0, which is 0. Okay, and the product then will give me 0. Okay, that means this limit, finally, yes, so limit of fx minus fx0 equals 0 as x approaches x0, which is limit fx equal fx0. Okay, so any function that is differentiable is necessarily continuous. Okay, so to summarize, so we have three categories. When for derivative, for function to be differentiable, so let's put it that as a remark. Okay, let's put this as a remark. What is it? Cursor. Right, here it is. So we are here. Okay. Okay. So to summarize here as a remark, to be so either when we have a function, either we have we have a few possibilities. Either we have f prime x0 finite. Finite, that means that we have a tangent. We have my curve and they have my tangent line. Okay, with slope f prime at x0. Okay, if I am at x0, so I have my tangent line. So that means my function is differentiable here, f differentiable at x0. Okay, either we have a discontinuous function. If it's not continuous like that, so here a function is not differentiable, because discontinuous. We said necessarily it must be continuous. Another situation where it's not differentiable, we saw it with the absolute value function. We have a corner, so we can have something like that, like that and like that. So we have two half tangents, for example. Okay, at this point x0, two half tangents, so not differentiable. But still we have okay, because we have a cusp here, still we have information. Okay, there is one situation we didn't saw. It's like the function square root. This square root function, you see, it has a behavior like that. At 0, there is a problem here. We have an infinite tangent. Infinite slope. Infinite slope, so not differentiable. Okay, so this is the case we have. Okay, so for the this was the example I wanted to explore. So let's do it here. So fx here is square root of x, and what about the differentiability? So let's compute f prime at x is the limit square root of x plus h minus square root of x over h as h approaches 0. So this is calculation. No, we forgot about the derivability. We need just to compute a limit. The techniques we know, because here if you try to substitute, you will get 0 over 0 and determinate form. So we need to work on our expression. So let's work on the expression by using conjugates. Expression x plus h minus square root of x times, let's continue here, times square root of x plus h plus square root of x over h square root of x plus h plus square root of x as h approaches 0. So here we know it will be x plus h minus x over h square root x plus h plus square root of x. Okay, so simplifying by h, we will get 1 over h simplify square root x plus h plus square root of x as h approaches 0. Now at this level, if I can substitute h for 0, but I will get 1 over 2 square root, okay, which will be 1 over 2 square root of x, but this has meaning is defined for x different from 0, okay, if x is different from 0. Okay, for if x is equal 0, so let's come back and try to find the limit. Now f prime at 0 will be the limit square root of h minus 0 over h. As h you substitute here, you see it will be then 1, so I can divide. So here necessarily I'm working, of course, h here. For this situation I need to work with h plus. Okay, I can take, but for this situation I can have an h smaller than, yes, negative, because I'm moving around x from the right and the left. Okay, for this case you have your x here, you have your 0 here, so x plus h, even h is x, you add an h negative but small, since it goes to 0, you remain here, your point x plus h, even h for an h negative, with an h negative, h approaching 0 will remain here between. So you can always take the square root, it is well defined. Okay, so okay, remain here, so this quantity is well defined. But here no, it cannot be, you have to work with h approaching 0 to the right. Okay, now we can simplify. We have square root of h over square root of h, square root of h, for example, which is limit of 1 over square root of h as h equals 0 plus, and this is plus infinity. Okay, so the slope is infinite. So f prime doesn't exist. F prime at 0 do not exist. F is not differentiable. F is not differentiable at 0. So f is differentiable on the domain 0 plus infinity, not at 0. Okay, and in the graph, as we saw here, we have an infinite tangent line. Okay, so we have an infinite slope, an infinite tangent, vertical tangent. Okay, the last point I wanted to give, there is a definition, important definition about yes, but when the definition, yes, notation. Let's do the notation quickly, and then conclude with a definition. It's important to know it. Okay, so let's do quickly here a definition. So just we will say f is differentiable on an interval EB closed, for example, like that. Okay, or E plus infinity or minus infinity B. Okay, or you can also A and B open from one side, open from one side, closed by the other side, if f is differentiable at each interior point of the interval. Okay, and if the derivative to the right okay, and if the derivative f so the derivative uh, derivative to the right or left, to the left, okay, exists at the point, the end point of the interval val at the end point that is included in the interval. Okay, that is included. Let's correct here. That is included in the interval. Included in the interval. Okay, so it's yes, it's correct. And the last thing, now that we know from f we learned to define a new function, we can also define a higher derivative. Okay, so from function f we defined derivative f prime. So we said how we computed using the limit. We explored the property of derivative sets. Okay, is smaller than continuous functions. What can happen? So we can have corners, we can have infinite slopes, we have discontinuous function, and or we have functions that are differentiable, they have line tangents. So geometrically, this is what we can expect. We saw that the derivative can give us here sign, the sign here give us information on the shape. Okay, and we explored the absolute value with corner, a square root function with a vertical slope, x3 normal. Yes, that's all. Okay. So the last, since we have a new function f prime, imagine f prime now is a new function. We can always derive it. Okay, we can derive it more and get more functions, new other functions. Okay, so let's put this one as notation. So we set the derivative, we know the derivative, we can derive now f second, what we call f second of x. It's the derivative, or we denote it also like that, of f. So it's just you take f prime, then you derive it another time. And yes, we can have higher derivative also. Y third derivative is y second prime. You derive it. This is, and of course we can continue like to the order n.